Today, we're going to move forward with our discussion of proofs and talk about direct proofs. Direct proofs are the most common type of proof that you're going to find. The reason for that is direct proofs are logically the most straightforward, and whenever we can do something very simply with logic, then we want to take the simplest route. So we have P of x and Q of x, two open sentences, and our goal is to show that the implication P of x, Q of x is true for every x in our domain. So we already know that if P of x is false for a value of x, then it doesn't matter what happens with Q of x, we have that the implication is true. So we're only concerned with the values in our domain where P of x is true. So what we do in a direct proof is we take some random element in our domain and we say P of x is true for that element. And then we show through a series of logical steps that Q of x is true as well. And when we do that, we've shown that the implication P of x implies Q of x is true. So along the way, we're going to use a few things. And this is not at all a complete list. So the math that you've learned up to date, things in calculus, geometry, algebra, all of those things, they come into play now. So you know a lot of mathematical facts, and you're allowed to use them here. So whenever you're not trying to prove the thing, you're allowed to use it. So things that you're allowed to use, some about the integers, we have that the negative of every integer is itself an integer. We know that the sum and difference of two integers is also an integer. And we know the product of two integers is an integer. Whenever you use something that's widely accepted as a fact, you don't need to justify it in any way. If it's something that's a little bit more off to the side and people might not be familiar with it, then you need to justify it. Another thing that you'll use in proofs a lot is definitions. So here's a couple of definitions. The first one is an integer is even if we can write that integer n as the product of 2 and some other integer k. So whenever we're talking about even integers, we can say by definition we know this about the integer. Similarly, we have a definition for odd, and we can do the same thing. So an odd integer, by definition, is one that we can write as the product of 2 and another integer plus 1. So we have both odd and even integers that we can use. There are going to be times when the implication that you're trying to prove is difficult, and you struggle to see the connection from P of x to Q of x and see what that logical flow of steps is going to be. When you're doing that, you're going to be taking a step back and you're going to develop a proof strategy. And instead of trying to write out a proof directly itself, you're going to come up with a plan of action. And then you're going to carry out that plan. And in the end, you'll end up with a proof, but it might take more than a proof usually takes 2 drafts. It might take more than 2 drafts to get there. And that's okay. For a proof analysis, sometimes you'll be presented with a proof, or you'll read a proof in your book, and you'll say, hey, is that true? And you should be questioning that. You should be trying to convince yourself of the logical flow of ideas in the proof that's given. And proofs are given in all kinds of books. If you go back and you look at your calculus textbooks, you'll find proofs there. So take a look at the proofs now. Start evaluating them. And as you do so, as you try and explain the proof in your own words and try and reflect on what the proof is really doing, you're providing a proof analysis. Both of these things are really important to be able to do. They're a good skill to have. So let's take a look at what a direct proof might look like. So we have a result that we're trying to prove. So the result is given. If n is an odd integer, then 3n plus 7 is an even integer. So our P statement is that n is an odd integer. So we're going to say, all right, we're going to say P is true. So we're assuming that n is an odd integer. And now from that statement, I need to show that since that's the case, then 3n plus 7 must be an even integer. So I can say since n is odd, we can write n equals 2k plus 1 by the definition of odd for some k, right? Then I can take the 3n plus 7 and I can plug in my 2k plus 1 to see what happens when 2k plus 1 is plugged in. So I end up with 6k plus 3 plus 7 simplified down. I get 6k plus 10. And I notice that there's a 2 in common with both of those factors. I pull it out and I have 2 times 3k plus 5. Well, 3k plus 5 is an integer. And so by definition, 2 times 3k plus 5 is even. So that means that 3n plus 7 is even, making Q true. Therefore, the implication is true. So that's a proof using even and odd. Here's another one. I'm not going to take the time to talk through it. I'm going to leave that to you to think through it and provide your own proof analysis. But take a minute, look at it, and of course we can talk about it later if we need to.